So in this lecture we will discuss about the plastic capacity of section estimates based on the combined loading. In the last lecture we understood that what would be the necessity of understanding the compact limit in a given section, how to estimate the compact limit or how to establish whether the section is compact or not, and we have understood that the section is established compact limit, then we need not have to consider the buckling effect in the analysis, one can straight away find the failure by yielding. Okay. Otherwise the failure loads at buckling is much lower than that of yielding, therefore all your failure phenomena which is applied for plastic analysis will not hold good if the section is slender or the section buckles. Okay. So buckling effect can be ignored provided the section is compact, and you can choose a section such that the compact limit is established. It means B by T ratio, D by T ratio, B1 by TF, B1 by TW can all be chosen in such a manner or fabricated in such a manner that the section remains stiff or compact, so that the buckling effect is not preluding the yielding effect in the material. Okay. Now before we move on to estimating the plastic capacity under the combined action of bending and shear, bending and axial, etc., let us quickly look at the summary for our interested designer. What would be the equations which are readily available in the literature? Let us look at this. So let us look into only about 3 types of sections: I section and box section. All are thin walled sections. Okay, all are thin walled sections. Even I is also thin walled. I am not drawing it here. Okay, let me draw that. And circular tubes. The standard dimensions are marked here. And I call this thickness as S, and of course this thickness as T. For this section, let us say this is my B and this is my D and this is T, and of course we know T is very less than D, it is a thin walled section. For this section this is the diameter D, and of course thickness of the section is T, and we also know that T is much lower than D. So we are looking for the plastic moment carrying capacity MP. We will also look for the axial load carrying capacity NP. We will also look for the shear capacity Vp, and we also look for the torsion capacity Tp. It is a summary for our understanding. Okay. So this is Bt H minus T plus S into H minus T by 2, sorry, H by 2 minus T the whole square of sigma y will give me my MP. This is A into sigma yp. This is area of the web. This is Vp. I am writing it here. Let me. This is shear capacity Vp. AW into sigma yp. Of course, for shear we are applying the von Mises failure theory, so it is by root 3, and for Tp it is 2 Bt square root. Shear and torsion are anyway connected to each other, we already explained that in the last lecture. And for this box sections, sigma yp, this is A sigma yp, this is 2 d t sigma yp by root 3, this is 2 d square t sigma yp by root 3. As far as the tube sections are considered, it is d square t sigma yp, this is A sigma yp, where is area of cross section. In my case, area of cross section is actually equal to pi d into t, okay. It is not pi d square by 4, the circumferential thickness, right, pi d into t into sigma yp. So 2 dt and pi by 2, just now we saw this derivation. So this gives a comprehensive comparison of most important commonly employed cross sections for members in marine structures, where I have a table which gives me MP, NP, VP, TP independently. Now what I am interested is, when the bending moment and shear force or bending moment and axial force are acting together, what is the influence on the plastic moment carrying capacity. When they are acting independently, this is what the table is, which we discussed so far, okay. We now discuss what is the combined action of this. Is that clear? Can I erase this? Let us look at bending and axial load together. So, we will take up a rectangular section, we will also take up an I section later. First let us understand this. Let us say the section is having breadth as B and depth as H. The section is subjected to an end moment which is MP comma n, I will come what is MP comma n, also subjected to an axial force which is NP comma m. I will come to that what it is. Now NP comma n is the reduced plastic moment capacity due to the presence of axial force N. We should say N, not NP, and NP comma m is the reduced, the important concept is reduced here, reduced plastic axial load capacity due to the presence of M. Okay, we are looking at that. The stress distribution looks like this. and the combined action it looks like this. Sigma yp, sigma yp, and let me call this distance as E by 2. Of course, this is positive and this is negative. This is A, which shows the stress distribution under the combined action of M and N. I split this into two parts. I say this is equal to two parts. One is because of M alone and that is because of N alone. I say this is negative and positive, and of course this remains as E by 2, and of course now this becomes E. Okay. B is due to bending alone plus this is positive, which is N alone. Actually this is NPM. So B indicates the stress distribution under M alone, and C indicates stress distribution under N alone. I am looking for the combined action which is A, but I will derive this in part and parcel of B and C. So I could call this as pure axial case and I could call this as pure bending case, is it not? M alone means pure bending case. Now I am interested in finding out the pure bending case, which I call as MP comma N, which is this. The pure bending case is given by a standard equation which we already know, because this becomes a depth of elastic core, okay, can be computed as below. Though we have done it, quickly we will repeat this. Let us say I have a rectangular section which has a distribution like this. We call this as elastic core, we already know this. Okay. Now I consider this as two parts. One is fully plastic, which is B and H, okay, minus the elastic part. The elastic part, this is fully plastic minus the elastic part, which can be done as M for fully plastic, which is not true but still is given by, this is B and this is H. So BH into h by 2. I should say, put it like this, BH by 2 into h by 2 of half, h by 2 somewhere in the center, and half of that is the CG of that particular portion, and we have twice of this, there are 2 parts. So that gives me BH square by 4, is it not? Whereas for the elastic portion, the elastic portion is I can superimpose this here, and we already know this is E by 2, okay. We can write this as B into E by 2 into half of that into 2 parts of that, which will give me B E square by 4. Therefore, I can now say this is nothing but, for this notation, which can be B h square by 4 minus B E square by 4 of sigma yp, okay. Which can be, I can remove this, B h square by 4 1 minus E square by h square, which is m, which you can call this as into sigma y, of course, which you can call mp 1 minus E square by h square. It is a standard relationship, because this multiplied by this is nothing but your mp. Equation number 1. NPM, which is pure axial layered course, in that case for this rectangular section could be simply B into E into sigma y. If you look at the drawing or the figure 1 which we made earlier, is the elastic part will have a depth of E by 2 and E by 2, which is E, the breadth is B and sigma yp, okay, which I can rewrite this as BH sigma yp into E by H, okay. I can write like this, B into H is the whole area of the section, so I can say this as A into sigma yp of E by H. A into sigma yp is NP into E by H, this is NPM, calls equation number 2. Now combining 1 and 2, simply by combining 1 and 2, we are now studying the effect of bending and axial force together, plastic capacity. So this is MPN, that is what we are addressing, okay. So I should say MPn by MP, which will give me 1 minus E square by A square plus NPn by NP the whole square will give me E square by A square. When I add these two, I will get 1, is it not? Okay. This is called PM interaction diagram, PM interaction diagram. This is called axial force and bending. You can try to plot this, it will look like this. If you try to plot M by MP and N by NP, and if this value is 1, this value is 1, look like this. So, I should say plastic capacity of the cross section under combined action of axial load and bending for a rectangular section. Which we call as famously PM interaction diagram. Here P does not stand for plastic, this is P means axial force and M is bending, okay, bending moment. Any questions here? Having said this, let us extend this concept to an I section. Same way we can do I section, because I section is nothing but sum of rectangles of members, is it not? We have seen for one rectangle, we are now going to see for sum of rectangles, okay. Let us do for I section. I call this as S and this of course as T, and this as B, and this as H. We call this as area of the web, and I call this as area of the flange. AF stands for area of the flange and AW stands for the area of the web. Let us say I have a stress distribution this is subjected to bending and axial force. So, the stress distribution goes like this. Okay, by the way, what is this axis called, where I am marking the stress 0? What is this axis called? This axis, 0 stress axis or equal area axis, okay. Let us say this is sigma yp, so sigma yp, and centroid of the section is somewhere here, and this distance is E by 2 as you had earlier, same manner. So, I would say now this section is equal to where this is also equal to E by 2, this is also equal to E by 2, subjected to moment only, plus wherever these two values are there, I have an additional section and the stress distribution, of course these are all sigma yp, will become like this. Yeah. So, sigma yp. So, already these are same as meaning as A, B, C. A is the combined action, B is the bending alone, and N is the axial load alone. So, this is what we call as 0 stress axis. Stress is 0 here. Okay. Let us assume that the 0 stress axis is at E by 2 from the centroidal axis as shown in the figure. Bending moment of the section is given as below. M is going to be MP minus, same equation I am using which we did for a rectangle, MP minus, there we said it is B E square by 4. Okay. Now, I will say S E square by 4, is that okay, because B in this case is yes of sigma y, equation 1. Axial force N is given by, what would be the value of N? Axial force N has to come only from the web, is it not? But that is the N part. N part is not acting on the flanges, is it not? N is only on the purely on the web. So, what would be the value? Area of the web into sigma y. So, I should say ES into sigma y, is that okay? E is this value actually, is it not, E by 2 E by 2, and S is the thickness of that portion. So, equation 2. Already we have an expression for NP, what we derived in the last application of a rectangle. So, I am going to rewrite using these two equations 1 and 2. So, combining 1 and 2, I will slightly modify this, see how we are doing it. This is how the standard form given in the literature. So, we are doing it like this. M is given as MP minus. So, I have ES sigma yp in terms of N here. I am going to substitute that here because I have ES sigma yp here, substitute that here and do some mathematical manipulation. So, after doing that I write this as N square by NP square. NP already we have, it is nothing but A into sigma yp. So A by A web alone, this for the entire section, okay, into S H omega square by 4 of sigma y. You can substitute back for NP separately and you will see automatically you will land up in 1 minus 2 or 1 and 2 combining, you will get the same equation of 1 and 2 here, okay. This is how it is being expressed in the literature, so I am giving exactly the same equation here. So simplifying further, we can say M by MP, I can call this equation number 3, 2 is here, 3. So rewriting 3 M by MP plus N by NP square of A by A W square ZW by ZP. Z is the section modulus of the web alone and ZP is the section modulus of the entire section, okay, is given as 1. Where ZW is the section modulus, is the okay plastic section modulus of the web, and ZP is the plastic section modulus of the complete section. I will remove this, I would like to retain this, or I can remove the figure, no problem. So for I sections you can compute ZP as follows. That is section modulus of the entire section, plastic section modulus of the complete section is ZP. So ZP is approximately equal to, because we are doing some adjustments, it is area of the flange H minus T, where H is the overall depth and T is the thickness of the flange alone, plus Z of the web. So area of the flange can be simply A minus AW by 2, because there are 2 flanges, into HW, H minus T will give you HW, plus Z of the web AW HW by 4, is it not? That is web alone. Now I can say there is AW HW by 2 here by 4 here, I can simplify, rewrite this and saying that it will become A by 2 of HW minus AW by 2 of okay of 4, is it not? Okay, AW HW by 4. So I can express ZP now as ZW of, that is okay, AW HW by 4 to A by AW minus 1. AW HW by 4 is already we know it is Z of the web, to A by AW minus 1, that is ZP. I already have the ZP value and ZW value in this equation here, which I call as equation number 4, I call this equation number 5. Now substituting 5 in 4, I can rewrite 4 like this, which is M by MP plus N by NP square 1 by twice of area web by A minus area web by A the whole square equal to 1. Now, equation 6 is the interaction diagram. Let me check this equation again. M by MP, N by NP square 1 by A web by A minus A web by A square is equal to 1. This is true for a specific condition where N by NP is much lower than AW by that is axial load capacity N is lesser than the web capacity. Web capacity is nothing but AW into sigma. If it is true, this becomes interaction diagram. If it is not true, for axial load capacity greater than the web capacity, that is AW sigma yp, then the equation goes slightly different. Let us derive that again. Stress diagram goes like this. Now, the difference between the 0 axis stress and the flange, this value is called as C. The offset between the top of the bottom flange to that of the 0 stress axis is given by an offset by name C. That is the combined action when the axial load carrying capacity is higher than the web capacity. Very simple. If the axial load carrying capacity is lower than the web capacity, obviously the 0 stress axis lies in the web. Okay. Since the axial load capacity is much more than the web capacity, it comes to the flange. It has come to the flange now. It is coming to the flange, okay, somewhere here. So this can be now said as a pure case of stress rectangles or stress distribution diagrams of plus so this is case A, a combined action, this is pure bending and this is pure axial, this is N and this is M, this is plus. See where C is the offset between the 0 stress axis and the inner flange. As shown in the figure. So, in this case now M will be equal to MP minus, as we did in the last case, BC, because this is C and the width at that is B. So, BC into HW plus C, is it not, because this is HW, height of the web, there is C added to it now, okay, HW plus C, of course plus section modulus of the web alone, okay, into sigma yp, and the axial force N, which is taken from the figure C, is nothing but area of the web. Now web alone is not there, you got some part of the flange also. So that is going to be B into C twice, is it not? There are upper and lower both, right, of sigma. So for a thin walled section, C is much lower than HW. C is very small compared to H, this is HW. C is much lower than HW. So, C square term and all will go away from here, we can neglect them, okay. So, combining the above, I can call this equation number 1 again, I can call this equation number 2 again, combining 1 and 2, we get M is equal to MP, because you have BC sigma yp, you got AW sigma yp, which are present in the equation above. I am just submitting them and then rearranging them, okay. So M is equal to MP minus N of HW by C plus ZW sigma yp. Further, okay, I call this equation number 3. Further, ZP in this section is approximately equal to ZW of 2 A by AW minus 1, is it not? That is what we have seen in the last derivation for I section, we have seen this, okay. So substituting back here, I now generate the interaction diagram. So now the interaction diagram between m and n is given by m by mp plus n by np of one by 1 minus aw by a, oh this is 2a, this is 2a here, okay, 2a minus aw by a by 1 minus aw by 2a of twice of this. This is okay. Let me write it slightly in a different manner. Minus, okay, minus aw by a twice of 1 minus aw by 2. Let me check. Is equal to 1. That is the interaction diagram now, okay, where in my case n by np is much greater than or equal to aw by a. That is the second case. Previous case was the other way, is it not? I can rewrite this equation back again rewriting equation 4 m by mp of, because I have got common terms I can rearrange them, 1 minus aw by 2a plus n by np as 1. That becomes the interaction diagram. I will plot this, then we will stop here. So, if you try to plot this, the interaction diagram looks like this. This is my m by mp, this is my n by np, this is my value at 1 and 1. So, obviously at aw by 2a or aw by a, when it is 0, okay, when it is 0 this becomes a linear curve, okay. So, it gets a straight line. I can call this as aw by a 0. For any other value the curve goes, I think I can do it in a different color, the curve goes parallel, then bulges out, then parallel and bulges out, parallel and bulges out for different values of aw by a of 0.6, 0.4, 0.2 and so. So, this is my plastic capacity of I sections under combined action of m and n for different aw by a ratios, okay. In the next class we look at the box section and the tubular sections, then we move on to plastic capacity of plates. We will talk about collision problems. That will conclude the module 1. okay. Any difficulty, any doubt here? Okay, thank you.